All right, so the first part of this is just the timeline of kind of the history of the atomic model. And we're not going to spend a ton of time on that. You're not going to get questions about who discovered the proton, who discovered the neutron. But it is kind of important for us to just get an overview of the background to understand where we are now with the atomic model. So all the way back 5th century, we had people theorizing that everything was made up of these really tiny indivisible pieces. And that's where we got our word atom from, because they called them atomos, which means indivisible. This held for hundreds of years, and we kind of skip ahead to the 1800s where we have John Dalton. And in 1807, John Dalton gave us the atomic theory that honestly holds up pretty well to be from over 200 years ago. He had 5 basic tenets of his theory. The first is all matter is made up of atoms, which are the smallest units of an element. We'll see in a second. We'll talk about how that last part, the smallest unit, is actually not true. Now we know we have protons, neutrons, and electrons. Number 2, all atoms of the same element are identical. We'll look at how isotopes kind of go against that. Atoms of different elements are different. That's absolutely true. Compounds consist of atoms of 2 or more elements combined in small whole number ratios. That's also true. They're not always necessarily multiples of one another. Sometimes we get those weird ratios in our big organic molecules, but they are always going to be whole number ratios. And then chemical reactions are rearrangements of atoms to form new products. Atoms are never created nor destroyed. So it is true that matter is never created or destroyed, and atoms are not created or destroyed unless we're talking nuclear chemistry. And of course, nuclear chemistry is something that was very unknown to Dalton and his time. So pretty good theory, holds true in a lot of ways, but here are some ways that we know now are different. So atoms are not the smallest. They are divisible. We do have things inside of them. Protons, neutrons, and electrons, of course. But atoms are the smallest things that take part in chemical reactions. Not all atoms are the exact same. So we know about isotopes. They have different numbers of neutrons. So we've got like carbon 6, carbon 7, carbon 8. They're all carbon. They all have 6 protons, but they have varying number of neutrons, making them isotopes. All atoms and molecules are in whole number ratios, as I mentioned before, but some complex organic molecules aren't in nice they're all in whole numbers, but they're not necessarily all in ratios. And then atoms can be created or destroyed in nuclear reactions, like we mentioned. So in the late 1800s, we start to discover the things that are inside of an atom. So the first was J.J. Thompson, who worked with a cathode ray tube. It's negative on one side and positive on the other. And when he passed an electric current, it goes from the negative to the positive end. But what he saw when he added the electric field was that some things were moving towards the positive side and away from the negative side. And if it's being attracted to positive and repulsed by negative, then it's got to be negatively charged itself. So that was how the electron was discovered. So he didn't know that there was also a positively charged particle. He just kind of considered the whole atom to be positively charged within these little negative particles embedded within it. You'll often hear this referred to as the plum pudding molecule, or the plum pudding model, excuse me. And then we did do an experiment. Robert Millikan figured out the exact charge of a single electron and the charge to mass ratio he used from Thompson. This is not super important to know. It's just another milestone within the atomic theory. So then we had Rutherford, who did an experiment with gold foil. He got positively charged alpha particles through a piece of gold foil, which is of course going to be full of little gold atoms, if we were to be able to see it, on the molecular level. And what he expected is when he shot this positively charged beam through, that most of it would go straight through, because he thought that mass was evenly distributed all throughout the atom. But what he actually saw was that some went straight through, but then a lot of the beam was deflected and some even bounced all the way back. And so what that must mean is that the majority of an atom is actually empty space. All of the positively charged mass is really located in a tiny densely packed part called the nucleus, and that positively charged particle is the proton. So now at this point, we have found our proton, our nucleus, and our electron. Another scientist figured out that some atoms have varying number of neutrons. Those are our isotopes. And then Chadwick found the actual particle that was neutrally charged and called it the neutron. And that's where the name Jimmy Neutron comes from, because Jimmy is a nickname for James, and James Chadwick is who found the neutron. So at this point, we have kind of our very basic model of the atom, where we know that it is mostly empty space. In the very center is our nucleus, where we've got our positively charged protons, and then on the outside are our negatively charged electrons. So we've got a very basic model. So in order to really start talking about electrons and more of our current model of the atom, we do have to make sure we understand what energy electromagnetic radiation is. And so electromagnetic radiation is just the way that energy travels through space, and it has a wave-like behavior. So because it has a wave-like behavior, it's going to have a wavelength, which is the distance between the two crests of a wave. It's going to have a frequency, which is the number of waves per second that pass a certain point. So you can think of this like, if here's my point of reference, how many times a wave goes past that point, how quickly that happens, is going to be my frequency. And so you'll see that it's per second. So frequency can be seconds to the negative 1 over second, or we have made our own unit of hertz that just represents seconds to the negative 1. And then the speed, all waves travel at the speed of light, which is this constant right here. And we can combine all of these together to get this equation. This equation and this constant are on your reference sheet. So we can do calculations to find either wavelength or frequency, as long as we have the other one, because our speed of light's a constant. Something else we see from this equation is that we've got an inverse relationship between wavelength and frequency. So the shorter the wavelength, we have a much higher frequency. And then, of course, the longer the wavelength, we have a much shorter frequency. You can also see this relationship on our electromagnetic spectrum. As the frequency gets higher, our wavelength gets lower. We can also use this information to calculate the energy, and we use something called Planck's constant, which is this number here, and that's also given to you on your reference sheet, as is this equation right here. So that equation shows us that the energy is equal to Planck's constant times the frequency. And so that tells us that energy is quantized, meaning that it's in exact quantities or little discrete units of size. And so we call these little packets of energy quantum, which is where we get that whole quantum model. This pointed us towards the idea that matter and energy are not distinct. So from all the videos that we watched beforehand, you should kind of understand this already. But before, matter was thought to be particles only, while energy was in the form of a wave. Matter, being particles, has mass and position. Energy is like a wave, so it's delocalized and doesn't have mass, and you can't specify its position. And now we really understand that it's kind of a combination of both. So our atomic emission spectra is just when our electrons get excited. So let's say we have an electron on this level, and our electron gets excited. Then when it falls back down, it releases a photon. And if that photon of energy falls in the electromagnetic spectrum in the visible region, then we can see it. Every element is going to have its own unique emission spectra. And so if any of you in honors chemistry did where you used a spectrometer and you looked at a maybe like a noble gas burning in a lamp, you would see the actual spectrum. So if you see here, all of our different atoms have unique spectra. This also shows us that we have those quantized amounts of energy because only certain exact light was being shown and there was nothing in this black area in between. So that proves our model that electrons are in energy levels that are very distinct and discrete. So this led to the Bohr model, which was great for the hydrogen atom, but it doesn't work for any other atom because the hydrogen atom only has one electron. So it was great for the hydrogen atom, and it's still important for our timeline of the model of the atom. But it shows us how, what I mentioned before, an electron can fall from one point, one energy level to a lower energy level, and when it does that, it releases a certain wavelength of light. If it's in the visible spectrum, we see it. If it's not, we wouldn't actually see it with our eyes. So all this idea of energy and light and matter come together with our wave particle duality, which we talked a lot about after we watched our videos and you answered questions about. But the idea is quantum particles, such as an electron, so that's why this applies to us, because an electron is a quantum particle, has both particle and wave characteristics.